we can point and say, look, Iowa State, we've got this great aerospace engineering. So of course we got to talk about rocket science. But the truth is, the reason we talk about these problems is it's really easy to motivate because it's intuitive. We're moving through a three-dimensional space. When we have problems on Earth, we tend to think more two-dimensionally. And so, okay, so we have this satellite, and we're going to launch it. And what we want to do is it's going to launch from a shuttle and settle into a Lagrange point. Now, what's a Lagrange point? Well, roughly speaking, you can imagine you have, say, a big celestial object, like, say, a planet, and a smaller celestial object, say, a moon. And big objects tend to attract things. We call it gravity. And so if you're near a planet, you get attracted to the planet. But if you're near the moon, you get attracted to the moon. But there are some spots where if you're just in the right position, the amount of pull from one is equal to the amount of pull from the other, and so you settle down and you stay stationary. So these are really nice locations. And these are very desirable locations to put a satellite, because once you get a satellite there, it stays in one spot. So if you look at certain images of, for example, the Earth, where it always looks the same, you know, the Earth stays exactly in frame and you see this nice motion, well, that's because you're seeing it from a satellite at a Lagrange point. Okay, so that's where we want to get to. We want to get to that special point. Now, the satellite has its own propulsion engine, which will be on from time t equals 0 to time t equals 1, and then will automatically turn off. All right, so we've got this propulsion system. It's going to be on for a little bit, and then it's going to turn off. Now, the Lagrange point that we want is located in a certain position at 3, 4, 2. So we know where we want to end up. And when the engine turns off, the satellite must be at a complete stop, because if it's still moving, it's going to start drifting out of that point. No, we want it to stay at that nice sweet spot. So let's translate this idea. Must be at a complete stop. How do we rewrite that in terms of math? Velocity equals 0. So velocity at the stop point must be 0, which we represent by a vector of all 0 entries. All right. And then we know the acceleration. We're given it to us. Acceleration is equal to that. So we have all these things. We know where we want to end. We know what our velocity is when we end. And we know what our initial acceleration is. What is it we're looking for? Well, we want to find the location and the velocity that the shuttle needs to have at launch to guarantee a successful placement. So in other words, we're setting two things. We're going to have where it launches from. We're going to make sure it's at the right location. And the thing we launch from also has the ability to move. We're going to make sure it has the right velocity at launch. So at launch is secret code for saying time t equals 0. So what do? Well, we start with our acceleration. We say that's 6t plus 2, negative 4, 12t squared minus 6. So, if I want acceleration, and I need information about velocity and location, what do? We integrate. Yeah, because the acceleration is related to velocity. In that velocity, if you take the derivative, you get acceleration. So if you integrate acceleration, you'll get velocity. So the velocity of the satellite will be, well, what's the integral of 6t plus 2? 3t squared plus 2t plus a constant, c. All right. Antiderivative, negative 4. Negative 4t plus another constant, d. And finally, 12t squared minus 6. 4t cubed minus 6t plus another constant. Now, we say, all right, do we have information about velocity? And the answer is we do. We say that it must be at a complete stop. Now, we said the velocity equals 0, 0, 0, but it actually, we could be more specific. The velocity when we reach our destination. So the velocity at time t equals 1. So, we can say that 0, 0, 0, which is the velocity at time 1, well, that's got to be equal to 3 plus 2 plus c. So that's 5 plus c, negative 4 plus d, minus 4 plus d, and 4 minus 6 plus e, negative 2 plus e. So we just have these three equations. 5 plus c equals 0, so that says c equals negative 5. 0 is negative 4 plus d, so d equals 4. And 0 equals negative 2 plus e, so e should be 2. So we can now update our velocity. In fact, we know what our velocity function should be. It's 3t squared plus 2t minus 5, comma, negative 4t plus 4, comma, and 4t cubed minus 6t plus 2. Now what? Integrate again. Integration is it's a technique so nice, we're going to do it twice. But because, if you integrate velocity, you get to position. And we usually call that, of course, position is denoted by r. Okay, I don't know. Rosition? Maybe. All right. So, what's the antiderivative? T cubed plus t squared minus 5t plus f, working our way through the alphabet. All right, next entry. Antiderivative of negative 4t plus 4. Negative 2t squared plus 4t plus g. All right, come to the last entry. Antiderivative of 4t cubed minus 6t plus 2. T to the fourth minus 3t squared plus 2t plus h. Now, what do we want? Well, we want to make sure we end at the right location. So, it better be the case that 3, 4, 2, that's our position at time 1. That's when the engines turn off. So you plug in 1. 1 plus 1 minus 5 is negative 3 plus f. Minus 2 plus 4 plus g. That would be 2 plus g. 1 minus 3 plus 2. 0 plus h. So we get that 3 has to equal negative 3 plus f. So that tells us f needs to be 6. 4 has to equal 2 plus g. So that says g should be 2. And 2 has to equal h. Well, that's a nice one. H equals 2. Sorry, what?
G should be negative 2.
Negative 2? I need 2 plus g to get me to 4? No, that's okay. I make stupid mistakes. Believe me, I've made some incredibly bad mistakes. So you should always be suspicious. Thank you for checking. All right, F, G, H. So that's our F, G, and H. So what is our position? Well, our position function, that's r of t, we can update. That's t cubed plus t squared minus 5t plus 6, negative 2t squared plus 4t plus 2, and t to the fourth minus 3t squared plus 2t plus 2. Okay, so we're now ready to answer our question. Because it says, what do you want? We want to determine the location. So the location at launch, time 0, would be r of 0, which is equal to, well, it turns out it's 6, 2, and 2. Because you get lots of zeros. Zeros, we like working with 0. So this is our location. And then our velocity, that would be v of 0. So we can come up here and plug it in. We're going to get negative 5, 4, 2. So negative 5, 4, 2, and that's our velocity at launch. So that's how we should have the shuttle moving to get our place just right. Just right. All right. Any questions? Good. Well, so as we mentioned at the end of our last session, we want to talk about distance. So we want to find the distance that a particle has traveled along a parametric curve from t equals a to t equals b. And so in particular, you can imagine that I have this curve moving through space, and we want to say, how far did the curve move along? So we're going to go back and do integration. Now this is sort of a Calc 2 refresher. How do we use integration? Well, what we do is we say we're looking for something, so let's break what we're looking for into small parts. And ideally, the parts are flat, because we really like flat things. Once we've broken our things into small parts, we're going to estimate each little piece, and we're going to use tools for flat things. And the reason we use tools for flat things is flat things are really easy to measure. So for instance, if I wanted to measure the distance along a straight line, easy. What do? Well, I say, what's the distance between the two endpoints? Unfortunately, if I want to measure things along a curve, hard, unless you somehow are able to straighten it out. All right, so that's why we like flat things. They're easy to estimate. We add all the pieces together, and then we say, all right, let's get a better estimate by making our chopping smaller. Really, when we talk about adding things together, that's what integration is. Integration is basically just really intense adding. We're adding up lots and lots of stuff. So for us, what do we have? Well, we have this curve. This is the dotted line. And what do? Well, we identify some points. So maybe we just identify just a couple of points here. We say, all right, once we've identified some points, instead of following the curvy part, let's just approximate it by a bunch of straight line segments. Now, all right, that seems easy enough. But it's not a very good estimate, because you can tell that the straight line segment loses something compared to the curve. But you can get a better estimate by saying, all right, no worries. What I'll do is I'll increase the number of points. And then you'll see that the loss is much smaller. And of course, if you increase to even more points, you get to the point where it's like I can barely distinguish now between the curve and this sequence of straight line segments. So what happens is, okay, we say, let's take our curve, we're going to break it up. And the way we break it up is we actually break up our time. So time is how we move along the curve. And so we're going to say, all right, so we're going to start at time, we start up here at time A, we end here at time B, we break it up, and when we break it up into finer and finer pieces. So, what's the length? Well, the length is the length of these straight line segments added up. And the way you find the length between two points is it's the distance formula. So if you recall the distance formula, that's the square root of x1 minus x0 squared, y1 minus y0 squared, and z1 minus z0 squared. And if you think about what's happening, you're looking at differences. So when you see the symbol delta, that's a capital letter delta. When you see that, you should think, oh, I'm looking at a difference between two things. So the distance formula is saying, okay, how much you change in x, square that. How much you change in y, square that. How much you change in z, square that. Add it all up and take the square root. So there we go. There's our approximation. Now what we're going to do is do something that says, all right, I want to make it look closer to an integral. So the way we do it is we say, let's divide everything by delta t on the inside, and then we're going to have a delta t on the outside of the square root. Now, the key step here is these are actually the same expression. If you square the delta t and bring it in, you'll see that all the delta t's cancel. But now we're saying, okay, this is like our small change in our input. Good. Now we say, okay, let's think about each little part. Delta xi over delta t. So I'm looking at how is x changing over time. And in particular, I want to think of delta t as being very small. So if I want to ask the question, what's the change in x over change in time when that's a very small change in time, what does that become? Well, it becomes the derivative. So change in x over change in time, as the change in time gets small, gets closer to the derivative, x prime. Similarly, change in y over change in time gets to y prime, and change in z over change in time goes to z prime. And now, say, aha, as we keep getting better and better, we get the following. this approaches what we call the integral. And really, remember, the integral is just a fancy way of saying I'm adding things up. So the summation becomes the integral. The delta t becomes the dt. And then the square root of x prime squared plus y prime squared plus z prime squared becomes the square root of x prime squared plus y prime squared plus z prime squared. You can see this nice translation. All right. Now, we should point something out. If you recall from Calculus 2, we did talk about arc length. In particular, we talked about arc length of a parametric curve in 2D. Well, do you remember the formula for that? Yeah, it's that. The square root of x prime squared plus y prime squared. So, it's not very surprising when you say, oh, so let's just throw in a z prime squared, and now we're good to go. Now, there is a different way to think about how do you find arc length. All right. So, let's think of arc length in terms of distance. Distance traveled. Now we're going to say the following. If I want to think about, if I want to think about the distance I've traveled, I can say the following. Distance is the integral of speed. That's not too surprising. If I want to know how far I've gone, if I know how fast I'm going at any given time, I can figure it out by just sort of saying, okay, add up my little time segments, a little bit of speed times a little bit of time, gives me a little bit of distance, then I integrate. Now, what do we know is equal to speed? Magnitude of velocity, right? So we can say, if I want to find distance, I integrate from a to b the magnitude of velocity. Because velocity is a vector, and it has two parts, direction and magnitude. And the magnitude is what we call speed. Say, okay, well, I happen to know what r prime is because I've been paying attention in class. R prime of t, that's this vector that looks like x prime of t, y prime of t, and z prime of t. And therefore, if I take the magnitude, I'll get that. So the magnitude of r prime of t is the square root of x prime squared plus y prime squared plus z prime squared. So if it helps, you can memorize it in that way. Think, okay, let me find velocity, and let me take its magnitude. That's what I have to integrate. Now we come to our favorite warning, maybe our least favorite warning, because we have to keep saying this over and over again. Square roots are challenging. They're hard to deal with. And there's a desire to say, I see a nice, easy way out, which is to say the square root of a plus b plus c, I'll just take the square root of each part and add it up. And let me emphasize the word, not. So when you're dealing with square roots, it's not as simple as, let me take the square root of each part and add it up. It boils down to the fact that addition and multiplication are very different things. When you're talking about square roots, at the heart, that's a multiplication type activity. And addition is an addition activity. They don't blend together nicely. You have to be careful. So what do you do with square roots? Well, there's a couple of things. The biggest thing we'll look for is, can we rewrite the inside as a perfect square? So that requires us taking a look and saying, all right, can there be some way to manipulate, apply identities, do expansion, rearrange terms, and get it so that the inside looks like a perfect square? So there are other things that we can do. Maybe some part can be pulled out. There's also substitution can sometimes work. You have to pay attention. There are things that can be done. But it's not going to be impossible. Anything that we ask you, it's not going to be impossible. But it will take some work. But that's all right. We like to work. Okay. So, now some examples. Suppose a particle's position is given by x of t is a half t squared, y of t root 2 times t, and z of t is log t. Find the distance the particle travels from time t equals 1 to time t equals 2. So the nice thing is we have the formula here again. So okay, So 1 and 2, this is the a and the b. So we can say, all right, we're going to integrate from 1 to 2, a to b, the square root of. Now we take the derivatives. What's the derivative of a half t squared? It's t. And now that's the derivative. We're going to square that. Plus, what's the derivative of root 2 times t? Root 2. And then we're going to square that. What's the derivative of log of t? 1 over t. And we're going to square that. All right, so that's the integral we have to do. So this is the integral, 1 to 2, of the square root of t squared plus 2 plus 1 over t squared dt. Now, we think and we say, okay, I have to work with this integral. There's something I have to do. And the best tool I have is to say, it would be fantastic, amazing, if what was inside that square root were a perfect square. Okay, that would be great. So we think back to what do perfect squares look like? Well, perfect squares, that's an a plus b squared. So I should have an a squared plus a 2ab plus a b squared. So one of the things I look for is I say, do I have 3 terms? And it's like, if I do, okay, that's a good sign. Then I say, well, there should be like a 2 in there somewhere, and I see a 2. It's like, oh, maybe this 2 is the 2 from the 2ab. And now we start thinking, okay, so this could be the a squared, so that would be a could be t. Over here, the 1 over t squared, that could be like b is 1 over t. But the thing is, what's here? There's no ab. Well, we could just try it out. The question is this true? If I put t times 1 over t, have I changed anything? No. It's essentially, it's a 1, because it's a 1. So, what do we have? We see that we can rewrite this. This is a perfect square. It's t plus 1 over t, quantity squared, dt. And now the square root of a square, well, it will become t plus 1 over t. So now we don't have any square root to deal with, and we're happy. All right, integral of t, a half t squared. Integral of 1 over t, natural log of t. And this is a definite integral. We don't need a c, but we need to evaluate from 1 to 2. We plug in 2, 1 half times 2 squared. That's a half times 4, which is 2, plus log of 2. Then we're going to subtract, plug in 1, a half times 1, which is a half, plus log of 1. Someone's saying log of 1 is 0. That is correct. And log of 2 is log of 2. That is correct. 2 minus a half? 3 halves are 1 and a half. So 3 halves plus natural log 2. All right. Well, let's try another one. Suppose r of t is 1 minus t squared minus 1, and t cubed. Find the length of the curve from t equals negative 1 to t equals positive 1. All right. That doesn't sound so bad. In fact, it looks even easier than last time. There's no like log of t or square root of t. That seems pretty straightforward. What's r prime of t? Negative 2t, 2t, and 3t squared. Okay, that's pretty nice. All right. So, what do we have? Well, we would want the integral, negative 1 to positive 1, of the magnitude of r prime of t, dt. Okay, so that's the integral from negative 1 to positive 1 of the square root of, and now we square these things, negative 2t squared plus 2t squared plus 3t squared squared dt. And we can clean that up. That's negative 1 to 1. So you'll get a 4t squared and another 4t squared. So that will give you a grand total of 8 of your t squareds. Then you get 9 t to the 4th. All right. Good. Now, how do we integrate this? Okay, so we can pull out t squared. Notice that this one can't be made into a perfect square. What's one of the clues you can't make this into a perfect square? There's only 2 terms. That is a great answer. That's the answer I like. Because if you look at a plus b squared, you should have 3 terms. This only has 2. Not enough terms. Okay, so we can't pull out. But someone said, we could pull out the t squared. I like this idea. Okay, so we pull out the t squared. And the square root of t squared? T. All right, so we get t square root of 8 plus 9 t squared dt. Now, how do we integrate this? We can do u substitution. Cool. So, what do we substitute? What's our u? Everything inside the square root. That's a great choice. It's a bold choice, but I like it. It's a great choice. Du, 18t dt. So, we got the t and we got the dt. So what I'll do is I'll write this as 1 over 18 du is t times dt. All right. So let's see. I'm going to do this integral off to the side as an indefinite integral. So we get that t square root of 8 plus 9t squared dt. That would become integral of 1 over 18 from this du term. And then the square root of 8 plus 9t squared would become square root of u, or u to the 1/2 du. The integral of u to the 1/2, by the way, what is that? U to the 3/2, and then you multiply by 2/3. All right. And then plus a c. And so that becomes 1 over 27 times u to the 3/2, but u, that's 8 plus 9t squared to the 3/2. Okay, so that says that this is going to equal 1 over 27, 8 plus 9t squared to the 3/2 power. Evaluate that from -1 to +1. All right, we're almost done. This is going to be a quick problem. Okay, 1 over 27, plug in 1. 8 plus 9, 17. We're going to have that to the 3/2 power. Then we're going to subtract, plug in -1. -1 squared, 1. 8 plus 9, 17 to the 3/2 power. 17 to the 3/2, subtract 17 to the 3/2, equals 0. All right. Well, maybe that's the answer. But that's kind of suspicious for a couple of things. If a particle, if I go from time t equals -1 to time t equals 1, and we say the distance traveled is 0, what should be true about the particle? It hasn't moved. Because if you haven't traveled any distance, you've gone nowhere. But here's something kind of peculiar. If you plug in where are you at time -1, it turns out that you're down here at 0, 0, -1. And if you plug in where you're at time +1, it turns out that you're up here at 0, 0, +1. So now we've somehow found a way. There's this parametric curve that we've discovered has this somehow magical property of transporting from one point to another point, but requiring 0 distance. Or perhaps we made a mistake. What do you think? Sorry, what?
You have to break the integral into 2 parts.
Well, we don't have to break the integral. But what was our mistake? We forgot the absolute value. That was our mistake. It was going from here to there. Because the square root of t squared is not t, it's the absolute value of t. And you can't see that. Okay, so let me rewrite it. The square root of t squared, it's good to rewrite it because it's good to say it again, is the absolute value of t. Because what happens is when you square something, you're always going to end up with a positive number. The square root will return a positive value. So regardless of what number you feed in, out is going to become something which is positive, or 0 if you plugged in 0, I guess. So you've lost the sign. So this is one of those things that says, just be careful, be careful. All right, so how do we fix it? Well, we fix it by saying, all right, what we really need is we need this absolute value added onto there. Which is why I sort of did it off to the side, because if we hadn't done it off to the side, you would have caught my mistake earlier. Now, we don't usually integrate with absolute value, and someone said, hey, you should break it up. And we could. How would we break it up?
Maybe go from -1 to 0, then 0 to 1.
Yeah, -1 to 0, 0 to 1. Well, we can save ourselves some work. Look at what we're integrating. This has symmetry. What kind of function is this? Is this function an odd function or an even function that we're integrating? It's an even function. And if you're integrating an even function, that says, if I'm integrating from like a negative a to a positive a, I can just double the result of going from 0 to a. And now, because I'm going to be in the range where t is positive, because this says t goes from 0 to 1, the absolute value I can drop. So, what changes? Well, if we come down here, we can say, all right, it's the same thing, but we're going to get now a 2 over 27, 8 plus 9t squared to the 3/2, but we're going to evaluate from 0 to 1, which says that we'll end up with 2 over 27. We'll still get 8 plus 9, which is 17 to the 3/2. Then we're going to subtract, plug in 0. 8 plus 9 times 0 is 8 to the 3/2. And 8 to the 3/2 really doesn't simplify, so there's our answer. All right. So this is one of those, be a little bit careful. Be a little bit careful. Just enough. Just enough. All right. Now another thing we're going to need in our later sessions is the following idea, which is what's called cumulative arc length. So cumulative arc length says, what's the total distance that you've traveled so far? And we denote this by s of t. So s of t says, all right, I'm starting at some initial time. Oftentimes it's 0, doesn't have to be. There's some initial time. We call it t naught. And it says, all right, how far have I traveled so far? What's the total distance I have gone? So you find that by, you integrate t naught to t of the magnitude of velocity. That's just another way to write r prime of t. So if you look at this expression, one of the things that you'll see is, suppose you take the derivative of both sides. So if I take the derivative of s, well, that's the derivative of an integral. And the fundamental theorem of calculus, and what is that? Well, the fundamental theorem of calculus, recall, it says the following. If I want to take the derivative of the integral from a to t of f of t dt, f of s ds, then that would be f of t. All right. So what you're doing here is you're saying, let's take the derivative of the integral from t naught, that's our a, to time t. And then the function, well, it's this function called the magnitude of velocity. And instead of s, we're just using this symbol called tau. You're going to learn so many Greek letters by taking math. It's great. You'll finally know what all these fraternities stand for. All right. So the outcome is this function on the inside, so it's the magnitude of velocity. So we're going to need this fact, again, for a discussion in a later session. Now, why do we care? Well, we can reparameterize our curve so that we say, look, I want to know my position based on how far I've gone. Not on what time it is, but how far I've gone. So it says, I want to know where I'm at time where I've gone a distance 3 units, where I'm at the time where I've gone a distance of 5 units, and so forth. So, as an example, we'll take a curve. It's a very nice curve. It's a helix. So cosine t, sine t, t. Now, there's a picture of the helix, and it has this shape here, but it's actually not too hard to figure out what it was, even if we didn't have a picture. Because think about just the two-dimensional part, the x and y. When you see the parameterization cosine t, sine t, what is that? It's a circle. So cosine t, sine t just revolves around. It's going around the unit circle. So you have this in the xy, this circling around. So now you say, okay, so in x and y I'm circling around. Then you have this z part, the z component, and that's just as you move up, as you circle. Because as time goes forward, you move up. So it's a circling plus a motion up. And that's what you see here. It's a circling plus a motion up. So that's the helix. So what we want to do is we want to find the cumulative arc length function, and then we want to reparameterize the helix as a function of s. So what do? Well, this is our position. So we have r of t. That's our cosine of t, sine of t, t. Our velocity will be the derivative. So what's the derivative of this? Negative sine t, cosine t, and 1. So the magnitude of velocity, well, that's the square root of negative sine t squared plus cosine t squared plus 1 squared. All right? Do we complete the square on this one? No. What can we do? Yeah, trig identity. Sine squared plus cosine squared has another name. And it's known as 1. And 1 plus 1 makes 2. So we get square root of 2. So this tells us that on this particular curve, the way it's been parameterized, it's actually going, in some sense, at a constant speed. Because the magnitude of velocity is constant. Now notice it's not going at a constant velocity, because what's changing with our velocity? Our direction changes. So you can have constant speed but not have constant velocity. All right. So we're now ready to answer s of t. So s of t, the cumulative distance, is equal to the integral from 0, and we know that it's 0 because we're told t not equals 0, up to t of the magnitude of velocity, which is square root of 2 d tau. Well, what's the integral of square root of 2? Square root of 2. And it'll be tau, but you evaluate from 0 to t, which means it's square root of 2 times t. So if I want to know how far I've traveled, because I'm going at that constant speed, it's just the speed times the amount of time. Now what I can do is I can do the following. There's this word, reparameterize. So that says, look, I don't want to have my expression anymore be a function of t. I want to have it be a function of s. So to get to that point, what we do is we come to our relationship. So I have here s as something involving t. We reverse that. We say, okay, I want to now write t in terms of s. So how do I get t in terms of s? Divide by root 2. So t equals 1 over root 2 times s. And now what I do is I say, okay, this right here, I'm going to replace t by this new term involving s. So what do we get? Well, we're going to end up with cosine, and now I replace t by 1 over root 2 times s, sine 1 over root 2 times s, and then t would be 1 over root 2 times s. And that's the new parameterization. Now, how do you use this type of tool? Well, you might say, okay, suppose I start on the helix, and given we have gone a distance of, anyone have a favorite number? 5 units on the helix. Where are we? So we can ask that type of question. I say, all right, I'm on this helix. I've gone a distance of 5 units. Where are we? Well, now the answer is you come to here, because this tells you your location based on how far you've traveled. So what do? The answer is you put in 5 for s. And given how closely my s's and 5's look to each other, it will feel like I haven't done anything at all. But I do promise these 5's and s's are different, so I'm going to try to make them look different. But that's the answer. So this is the kind of question that you might see that involves the cumulative arc length function. It says, I've gone so many units. Where am I? Well, if you have the cumulative arc length function, you can answer that question. Essentially what's happening is you say, okay, I've gone so many units. What time does it take for me to get to that? All right, now that I know that time, let me figure it out. All right. Find the distance traveled along the curve. 1/5 t to the 5th minus 1/2 t to the 4th plus 1. That's the first entry. Root 5 over 4 t to the 4th plus 3 is the second entry. And 4/9 t to the 9/2 plus 7 for 0 less than or equal to t less than or equal to 4. Well, interesting. All right. So by now we know the formula, distance formula. We know we're going from 0 to 4 because time goes 0 to 4. We're going to take a square root of, and now we go through and start taking derivatives. What's the derivative of the x entry? T to the 4th minus 2t cubed. And then we're going to square that. Plus, now we go to the next entry. What's the derivative of the next entry? Square root of 5t cubed. That's an unusually specific derivative, but okay. Square that. Go to our last entry. Derivative of 4/9 t to the 9/2. 2t cubed. Let's see, what is that? 36 over 18, yeah, I think that's 2. 2t, oh, whoops, not 9/2 to be, sorry, 7/2. Yes? 3.5 squared. Am I close? All right. Well, or as they say, what do you think? What should we do? Yeah, probably we should expand at least the first term, right? So this would become square root of t to the 4th square, that's t to the 8th, minus 2ab. So, the t to the 8th, that's like the first term, a squared, then minus 2ab. So that become 4. T to the 4th times t cubed is t to the 7th. The 4 comes from 2 times 2, really 2 times negative 2, and then the powers add up. Then plus 4t to the 6, square root of that term. The middle term is 5t to the 6, because you square it. And the last term is plus 4t to the 7th. Now, does anything simplify? 4t to the 7ths cancel. And of course, these two combine. So we get 9t to the 6. So we have t to the 8th minus 9t to the 6. How do we proceed? What's our next step? We might as well pull out t to the 6. Square root of t to the 6. Man, I've really made you like paranoid, right? Oh, it's absolute value. You're not going to fool me twice. Okay, do we need the absolute value in this problem? No. What's special about this problem versus the other problem? We started at 0. Time is always positive because time goes from 0 to 4. So, but we check. We check. You know, fool me once. Shame on me. Fool me twice. It's not nice to fool people. That was the words of one of our former presidents. All right. T squared minus 9. All right. Cool. How do we integrate this?
Say u sub t squared.
Yeah, u substitution. You might be like, oh my gosh, this looks like a trig substitution coming. But we're never going to do that to you. We're not that kind of instructors. We're going to be like, you have the tools. Calc 1 tools are enough. So, proceeding as we did before, u should be t squared minus 9. Well, what's du going to be? 2t dt. Now, since I don't like the 2, I'll move it over there. So half du is t dt, which is the same as du equals 2t dt. The problem is we don't have any t's. We have this t cubed. Ah, yeah, t cubed. That's t squared times t. So one of the t's is going to attach to the t dt. But now I have another problem. What do I do with that t squared? I can rewrite t squared in terms of u. T squared is u plus 9. So, updating. The t squared becomes u plus 9. The square root of t squared minus 9 becomes u to the 1/2. The t dt becomes a half du. Is there anything else we need to do? Yeah. First off, I need to realize that I put minus 9 when it should be a plus 9 because this is a plus 9, which means this is really a minus 9. I was getting paranoid. Okay. Yeah, we need to change our limits of integration. What are our old limits? Well, we went from time equals 0 to time equals 4. Those were our old bounds. Our new bounds, well, at time equals 0, what is u? U is 9. At time equals 4, what is u? 25. So, we get this is 1/2. We can pull the constant out. This will be u to the 3/2 minus 9u to the 1/2 du, going from 9 to 25. So, that's something we can integrate. So we get 1/2. Integral of u to the 3/2. 2/5 u to the 5/2 minus integral of u to the 1/2. It's going to be a u to the 3/2. And then what goes in front? Well, it's going to be 9 times 2/3. So 6. Yes? Evaluate this from 9 to 25. All right. Well, we're almost there. I can pull the 1/2 through. So this is 1/5 u to the 5/2 minus 3 u to the 3/2. And then we're going to evaluate from 9 to 25. So we get this is 1/5 times 25 to the 5/2 minus 3 minus 3 times 25 to the 3/2. Subtract 1/5 times 9 to the 5/2 minus 3 times 9 to the 3/2. Now we could simplify this even further. This is perfectly fine. One thing we could do, for example, is say, well, 25 to the 5/2, we just have to find what 25 to the 5th is. No, I don't want to do that. Wait, we can do something else. We can say, what's 25 to the 1/2? That's, okay, that one we can do. And then 5 to the 5th, of course, is, that's right, 3,125, exactly. You know, well, okay, maybe we'll just stop there then. All right, and that's a perfectly fine answer. Once more to the algebra, dear friends, once more. Find the length the particle travels along the curve t squared sine of t minus t squared cosine t plus t squared minus 17. Now notice we've actually written this in a different way. This is in the form where we have the I, j, k. So this is translating into our other notation, t squared sine of t minus t squared cosine of t, and then t squared minus 17. You should be comfortable with either notation, and you should also be comfortable with switching back and forth with the notations. So we have here as our x of t, our y of t, our z of t. So, what do we need? Well, let's take our magnitude of r prime of t. That's the square root of x prime of t squared plus y prime of t squared plus z prime of t squared. All right. Square root of x prime, product rule. All right, the root of t squared sine t, that'll be the root of the first, 2t times sine t, plus t squared times the root of sine, which is cosine. And then we're going to square that. All right, plus, okay, minus 2t times cosine t, and then minus t squared times the root of the cosine, which is minus sine, turning into a plus. There we go, sine t squared. And then plus 2t squared. All right. So that's equal to the square root of. All right, here we go. 4t squared sine squared t. 4t squared sine squared t. Plus, now the cross terms. So there will be, this was your a squared, 2ab. So 4, because it's 2 times 2, and t squared makes t cubed, and then sine t, cosine t, plus that squared, t to the 4th, cosine squared t. All right, well, now we go to this term. Well, let's square it. So we're going to get 4t squared cosine squared t. I'll put it right underneath. 4t squared cosine squared t. The cross terms. Well, again, 2ab, but because of the minus, it's going to be a minus here. Then it'll be 4, because 2 times 2. T and t squared makes t cubed. Cosine t sine t. And the last term, t to the 4th sine squared t. And then finally, there's a 4t squared. All right, this plus all that plus 4t squared. Good. Now, if we're good people, we've been living a good, clean algebra lifestyle, nice things should happen. Well, nice things do happen. These cancel out. Because the only thing that's different is the sine times cosine versus cosine times sine. Same thing. Okay. But even more happens. Notice here, you can pull out a 4t squared, then you get sine squared plus cosine squared. Well, that's 1. Over here, you pull out t to the 4th, cosine squared plus sine squared. Again, that's 1. So, what do we end up with? Well, we end up with the following. Since this is 1 and that's 1, we get 4t squared plus 4t squared. So that is 8t squared, and then plus t to the 4th. All right, well, we're kind of back into our normal game. So now we're saying, all right, what's the length? Well, the length will equal the integral 1 to root 8. It's an unusual choice, but who knows? Maybe it'll become more clear. Notice, before we get into the integral, we're going to have t be positive, and I can pull out a t squared. And this is a trick we used a lot today. I don't want to give the impression it always happens. Well, this is a trick that does happen. I shouldn't call it a trick. A beautiful math fact. A beautiful math fact doesn't always happen, but it's useful for today. It shows up a lot. So t square root 8 plus t squared dt. Now here, well, we'd go and proceed similarly as before. U equals 8 plus t squared. Du would be 2t dt. So I can put a 2 and a half. So I get the 2t there. Now, what do we get? Now, this will be equal to, update the bounds. These are t bounds. So if t equals 1, u would be 8 plus 1 squared, meaning u would be 9. T equals root 8, u would be 8 plus square root of 8 squared. That's 8 plus 8, which is 16. We have the 1/2 in front. The 2t dt becomes du, and the square root of 8t squared becomes u to the half. So this becomes 1/2 times u to the 3/2, because I add 1 to the exponent, then I multiply by 2/3. The 2's will cancel, that's good. And we're going to evaluate from 9 to 16. We say, all right, so this is 1/3 times 16 to the 3/2 minus 9 to the 3/2. And I think this one is simple enough we could probably actually go all the way. For example, what about 16 cubed? Well, 16 cubed is 4,096, right? Probably thinking, yeah, of course it's 4,096. Well, probably it's easier to think of this as 16 to the 1/2, and then we cube it. Similarly, 9 to the 1/2, and then we cube it. Because 9 cubed, well, 729. But who remembers that? But it's easier to remember 9 to the 1/2. All right, so what would that be? So that's 1/3. 16 to the 1/2 is 4. 4 cubed, 64. 9 to the 1/2, 3. 3 cubed, 27. So 64 subtract 27. Well, that would be 1/3 times 37. Or I guess we would write it as 37 over 3. And so therefore, that's how far we traveled. Good. And you'll oftentimes see this when you ever have things where multiplying something by cosine and multiplying something similar by sine, where when you square things out, you get cancellation of the cross terms, and you get cosine squared plus sine squared combined together. You should always be suspicious that things should be really nice. Not because that things are always nice, but because we want you to celebrate the beauty that is math. So we're going to show you things which are nice. All right. Well, that's a good problem. And we'll do some more problems next time.